Junctions always have some capacitance associated with them. I've dragged out our old picture of a p-n junction on the left side of this slide, and I've included the two equations we used to calculate the width of a p-n junction on the bottom of the slide. These equations indicate that the width of a p-n junction changes as Vd, the bias voltage across the junction, changes. That means forward biasing the junction by increasing Vd results in a narrower depletion region. So if this is our equilibrium region, then forward bias makes the region narrower. And reverse biasing the junction by decreasing Vd does the opposite, results in a wider depletion region. That's all old news to us. We've talked about changing width of a depletion region before, but there's fixed charge inside of a depletion region. So when we make a depletion region narrower, we are changing the total charge stored in the depletion region. The width goes down, so the charge goes down, and that can be thought of as differentially as some dq dv value. The opposite is true when we reverse bias it. The width goes up, so the charge goes up. That is also a dq dv value. You're probably used to the linear capacitance formula Q equals CV, which says there's a linear relationship between voltage and stored charge. Charge stored in a depletion region isn't linear. The width varies as the square root of the voltage. So we need to use a differential definition of capacitance. C is equal to dq dv. If we do that, we can see the capacitance is large when the depletion region is forward biased, so it's large here, because the slope of this square root function is going to get higher as the argument gets smaller. Similarly, we can tell that the capacitance would be small in reverse bias because this argument would be large, and accordingly the slope of the square root function would be low. So if we plotted that, we'd find that the capacitance versus bias curve for a p-n junction looks something like this. The capacitance of junctions increases as the total diode signals increase. And the junction cap is rather hard to model, but one common equation for this expression is given here, where CJO is some reference capacitance that is in the femtofarad to picofarad range depending on the manufacturing process, and VBI is the built-in voltage that we calculated by integrating the junction charge way back in the day. Other versions of this model will use a cube root on the bottom here, or some other fractional exponent for the denominator. And modern transistors are modeled by just measuring them carefully and storing all of the different capacitances at different bias levels in a lookup table. This CJO value, by the way, is on the order of femtofarads to picofarads, depending on the manufacturing process, more commonly in the femtofarads range. One way students like to remember this capacitance curve is thinking that the capacitance is high when the junction is narrow, and that seems kind of like a normal capacitor, where the capacitance is epsilon naught A over D, and so as you get your plates closer together, the capacitance goes up. That's a fine way to remember it, but it isn't actually accurate to the physics that are going on inside of the depletion region. Our capacitance doesn't go up because we're storing charge on the outside of the depletion region. The charge is in the depletion region. And our capacitance is going up because the rate of change of that charge is higher when the depletion region is narrower. We can convert this capacitance curve into a large and small signal model for a diode. Large signal, the diode looks like the diode we know, in parallel with this CJ curve up at the top of the page. Small signal, we have our differential resistance for the diode, and we pretend that our junction cap doesn't change when we put a small signal across a diode, instead just treating it as the value of the junction cap at the large signal resistance. So this is a nonlinear capacitor that changes with signal. This is a linearized capacitor at the large signal bias voltage. Alright, let's put this model to the test. We're going to use it to figure out if we should forward or reverse bias photodiodes. Photodiodes are light-sensitive diodes that are often used as receivers in telecommunication systems. As a result, you really care about how fast you can change the light signal at the input of the diode and still measure a signal, because that sets the data rate of your communication system. We can make a small signal model for photodiodes, and we've done so here. The light signal shows up as a current source in parallel with our normal diode model, which is a differential resistance in parallel with our junction cap. So two quick ways you could imagine making a receiver are pictured over on the right of this slide. One has the diode reverse biased and the other has the diode forward biased. In both cases, we're biasing the diode with a resistor and hoping that the light current source drives the I light from our small signal model will drive into this resistance and make some voltage V out. Pause the video and figure out the -3 dB bandwidth of the response to I light, and write down whether you think we should use the forward or reverse biased setup. I've drawn the small signal model that represents both circuits here and calculated V out as a function of I light. I found this relationship by noting that I light was going to drive into the parallel combination of RD, R, and CJ, which form the input impedance of the photodiode. That means the -3 dB bandwidth is given by 1 over the time constant, or in this case 1 over R parallel RD times CJ in radians per second. And you divide by 2 pi to get that into hertz. So, just quickly summarizing, this is tau, your bandwidth is 1 over tau. I contend we should reverse bias the diode. It'll make CJ smaller, which increases our bandwidth. It'll make RD bigger, which increases our gain, and there's no DC current, which reduces our power. However, if you have a slowly varying signal, sometimes forward biasing the diode makes sense so that your output voltage is referenced against 0 volts instead of against the supply. That was a pretty common configuration in E80, which indeed had very slowly varying light signals. So in summary, the depletion width of a PN junction changes with applied voltage, which means that the stored charge inside of the depletion region changes too. C is equal to dq dV, so there's a capacitance Cj at PN junctions. And the junction cap at the junction increases with forward bias. So the plot looks like this, and the expression for it looks like this.